Okay, so last time I kind of gave you an overview about Python programming, but that is not the sole goal of this course. The goal of this course is to teach you discrete mathematics and to expose you to the fundamentals of a lot of the mathematics that you've seen in the past. So in order to talk about the fundamentals of mathematics, when we talk about proof writing and algorithm design, we need to spend 2-3 courses on propositional logic. So lecture 1, introduction to logic, and more specifically, I should say propositional logic. Okay, and anytime we encounter a new topic, we're going to have to first deal with a lot of definitions. So the first half of the class is just going to be me telling you new definitions and giving you examples of them. Let's go ahead and begin with our first definition. So a proposition is a declarative statement that is either true or false. True, always going to denote by a capital T. And false, capital F. All right, so that's the definition of a proposition. Statement that declares something, and this something that it declares has a truth value. And the truth value is one of these two things, and exactly one of them, true or false. Okay. So for example, UHC is a public university. Okay, so that is example of a proposition, and the truth value of this proposition is true. Another one would be 2 + 1 = 4. Another proposition. And the truth value of this proposition happens to be false. Okay. Pretty straightforward, right? Just the statement declares something, and you can decide whether or not it's true or false. It's a proposition. Okay. Now, propositions will be the items, the objects that we work on during the course of our section on logic. Okay, so just as in arithmetic, you have numbers and you have arithmetic operators like addition, subtraction, multiplication, division. We're next going to define operators on propositions. Okay. Now, in order to do that, we should simplify these sentences, these propositions, and we're going to represent them as variables and then work on these variables. So a little on notation. We will typically use lowercase letters to denote propositions. So lowercase letters. To denote propositions. Okay, so for example, we could say that this proposition here, we can call that lowercase p. UHT is a public university, denoted by P. And we could say that this proposition here, 2 plus 1 is equal to 4, call it maybe Q. And you'll see that, well, I will typically denote propositions by P, Q, R, S, T, these letters. Okay. Okay, so next we need another definition. So the negation of a proposition P is the proposition it is not the case that P. Okay, and this will be denoted not P. So this reads not P. Okay. Yes. Just not P.
Is that a 7 or is that like
Oh, this is an arrow pointing. Oh, the sign, the symbol.
Yeah.
Yeah, this is just the negation symbol, not P. It's a little. Already closer to you. Just let's see.
Uses the hyphen in the keyboard.
Oh, I see. Okay, so if we look at this proposition P here, UHT is a public university, then the negation is it is not the case that UHT is a public university. Okay. Or UHT is just simply not a public university. That's the negation of P. The negation of Q would be 2 plus 1 is not equal to 4. So what do we notice about the truth values of the negation and the original? Right, if the original statement is true, then if we negate it, the statement becomes false. If the original statement is false, the negation of it is true. Okay, so very important fact for propositions. There is a dichotomy between the original and the negation. They have opposite truth values. And we can represent that notion with what's called a truth table. So let's see if I can squeeze it in here. That's P. And this is not P. And this whole thing together is a truth table. If P is true, not P is false. If P is false, not P is true. Okay, so that's just a way to schematically show the possible truth values for a given proposition. Okay. Okay, so the negation of a proposition, you can think of it as just like an operator on a given proposition. The proposition, you can take the negation of it, you get a new proposition. Now, as in arithmetic, you have numbers, and maybe you can look at the negative of a number, it could be like the negation, maybe. You can also operate on numbers with other numbers, right? With addition, for example. Well, we're going to do the same thing. I'm next going to define operators between 1 and 2 or 3 or more propositions. Okay, and there's only like 4 basic ones, and I'm going to write them out as a truth table to save time. Right, so give me a second to write this table out. So we're going to look at proposition P, at proposition Q, and the possible combinations of true and false, there's 4 of them. Right? You can have true and true, you can have true and false, false and true, and then finally false and false. Those are all the possible combinations of truth value between any 2 propositions that you encounter. Okay. All right. The first proposition or the first operator between P and Q, I'm going to write like this. And this is called the disjunction. The disjunction between P and Q, and it reads P or Q.
So that's a arrow pointing down.
Yeah. So this will be P or Q. All right, and let me give you the truth values. Okay. Those are the truth values for those combinations of P and Q. So how would you define it? Someone tell me how you define the disjunction between P and Q.
If both of them are true, so that one is gonna be true. If on the other ones, if one of them is only true, then it's gonna be true. And the last one, if both of them are false, it's gonna be false.
Right. How could we make that a little bit shorter? We could say
It's false. If it's false, everyone is true.
I think the best way to say it maybe would be the disjunction between P is Q is true whenever at least one of them is true and false otherwise. Right? That's one way that you could define it. Or you could say the disjunction is only false when they're both false. It's another way of thinking about it, right? To shorten it up a little bit. Okay, so the next one is called the conjunction. And this reads out P and Q. So you'll rarely ever hear me say disjunction or conjunction. I'll typically say or and to represent them. P and Q. All right, so let me give you the truth values for that. So how would you define the conjunction between P and Q?
Should be true, true, false, false.
But with words, how could we write out a definition for it?
It's true when both are true, it falls otherwise.
There you go, that's it. It's only true when they're both true and false otherwise. Okay, so it's like, let's look at the disjunction and conjunction between these two propositions here, which we have on the board. So the disjunction would be the statement UHD is a public university and 2 + 1 is equal to 4. Oh no, that's the conjunction. So what's that truth value? Right, UHD is a public university and 2 + 1 is equal to 4. That's false, right? But the so the disjunction, UHD is a public university or 2 + 1 is equal to 4, that's true, because at least one of them is true. So I should mention that what we're doing when we take an operator and use it between propositions, these are called compound propositions. When you have one or more propositions, if you have 2 or more propositions strung together with operators, it's a compound proposition. All right, so the next one. This is called the conditional. Okay, and this reads if P then Q. Or it also reads P implies Q. I should probably make a little bit of fuss about the notation here or the terminology for the conditional. So if P then Q is one way to say it. Another way would be P implies Q. And then here, in this instance here, P is called the hypothesis. And Q is called the conclusion. Okay. Now let me write out the truth values for these guys. So there are the truth values for that. So how would you define the conditional if P then Q?
It's false when P is true and Q is false and true otherwise.
Right, or another way to say that using this terminology up here is that the conditional is only false when you have a true hypothesis and false conclusion. That's how I would think about it. Okay, and it's true every other time, which throws people off, but maybe since most of you program, I can explain it a little bit. So like, let's look at like Q implies P here with these examples. So how would we read that? It would be if 2 + 1 is equal to, well, let me come up with another one. Maybe R. I'll say R is need a proposition. Maybe like the Earth is a star or something like that. Okay. So let's look at if Q then R. So how would we read that out loud? It'd be, so if 2 + 1 is equal to 4, then the Earth is a star. That's a true statement, because the hypothesis was false. Think about it in terms of like conditional statements in programming languages. If you have an if statement followed by code that's going to break, that if the if statement never occurs, the code still runs fine. Right? It passes by as true. So false hypothesis always leads to a true statement. It's what's called vacuously true. It's never tested. You never get to test the conclusion. Does that make sense?
Yeah.
Okay. But if I say if UHD is a public university, then 2 + 1 is equal to 4, the hypothesis is satisfied. You have to check the conclusion, and then it becomes false. Right, so that's why if you have a true hypothesis and a false conclusion, the whole statement, the whole compound proposition is false. Okay. And then obviously true implies true. The true hypothesis, you go into the statement, you check the conclusion, it's true, it evaluates the true. Right, so that's the conditional. Very important for probably obvious reasons to people to program. Okay, the next one, the biconditional. So this is P if and only if Q. That's how you would read that out. P if and only if Q. P if and only if Q. Okay, so what are the truth values for this? Well, true, false, false. So how would you define the biconditional between P and Q?
If P = Q is true. Only when they
Yeah,
have the
more or
same-
less, but we don't know what equals means yet in terms of propositions.
It's only true when they have the same values.
Right, so
It's false when they.
right, so I would just define it as the biconditional is true whenever both propositions have the same truth value and false otherwise. Okay. Right. So these are the basic operators. There is one more that you'll read about in the textbook when I assign the readings today, with you later. The exclusive or. Okay. But for our purposes in class today, these are the ones that we will focus on. Okay.
Professor,
Yes.
I don't mean to backtrack, but earlier you said when we have more than one or more propositions, it's called a composition.
It's called a compound proposition. So this, that, and that, those are all compound propositions. Yeah. But really, they're just other propositions. Like when you take when you string together a bunch of propositions, you get another proposition. Okay. with whatever operators you choose to use. And now that we have the basic operations that we can do between propositions, we can discover new relations, new logical equivalencies between compound proposition and compound proposition. But in order to do that, we need to know what it means for propositions to be logically equivalent. And that's the next definition. So compound propositions, or you can just think of them as propositions. P and Q. So P and Q could themselves be compound propositions. They could be any combination of propositions together, but I'm just representing them by a single letter. So propositions P and Q are logically equivalent written P triple equal sign Q whenever P if and only if Q is always true. Okay. So whenever the biconditional always is true, we say that the two propositions are logically equivalent. And if you think about the biconditional is just another way of saying if it's always true, that means they always have the same truth value. Like thinking back to how we defined it, right? It's true whenever they have the same truth value. So if it's always true, then they're equivalent, basically. And we should look at a non-trivial example, like a little bit more complicated example to kind of illustrate the point. So I claim that if P then Q, I claim that's logically equivalent to not Q then not P. That's what I claim. These should always have the same truth value and notice it. Okay, so how can we show this? Well, we can use a truth table. So the Q, we can have true, true, false, true, false, false, and then false, true, and then false. Okay. So then, if you look at if P then Q, go in that column, we get true, false, true. And if you look at not Q, implies not P. So if we kind of careful when we fill in this column, so not this implies not that, not this implies not that, and so forth and so on. So the first thing would be false implies false, which is true. False implies true, which is true. Wait a minute, did I do that wrong? Oh, this is true here. Let me switch it up. Yeah, I repeated one of the rows. It should be true, 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 false, false, true, false, false. So in that case, true, and then this will be the false. Yeah. So again, let's go back and look at this column now. False implies false is true. True implies false is false. False implies true is true. Right? Anytime you have a false hypothesis, it leads to a true thing. And then true implies true. And now, if we look at the biconditional between this and this now, If P, then Q. If and only if not Q, then not P. Okay. And the biconditional is true whenever they have the same truth value. So true, true. Okay, that'll be true. False, false. That'll be true. True, true. That'll be true. True, true. Notice that everything here is true. So since everything is true, that is logically equivalent to that. And it's because they always have the same truth value. Okay. So in fact, we probably should introduce another definition to describe something that's always true or something that's always false. Okay, so more definitions. Oh, before I move on too far from that, I should tell you what this is called. This is called the contrapositive. With P then Q. As we'll see in a later lecture, the contrapositive of a conditional can be very useful because it has the same truth value as the original conditional.
Is there time for you to explain more about that?
Okay, yeah. No, you're good. Thank you for stopping me. All right, so what would you like me to, where would you like me to start?
The P, therefore Q.
So if P then Q?
Yeah.
So this is the definition of the conditional. True implies true is true, true implies false is false, false implies true is true, false implies false is true. The only time the conditional is false is when you have a true hypothesis and a false conclusion. That's the only time.
So when it's both not P or not Q, they just flip.
So let's look at it one at a time. So not Q implies not P. So not this implies not that. So false implies false, true.
Yes.
True implies false,
False.
false. False implies true. True implies true, true.
And the other one's just both results matching each other.
Yeah, so then the biconditional checks, okay, do they have the same truth value here? They do, true. Same there, true. Same there, true. Same there, true. And this is how we define logical equivalence. When the biconditional between two propositions is always true, then we write that they're logically equivalent. So that's how we define logical equivalence with propositions. Now, we should introduce a way of describing something that is always true with a single term. So, again, a definition. There's like a few parts to it, actually. Maybe like one. A proposition that is always true is called a tautology. All right, so now that we have terminology to describe that, we know what logical equivalence is. It's when the biconditional between two propositions is a tautology. Okay. So, two maybe. A proposition that is always false is called a contradiction. And then finally, if you're neither, you're called a contingency. So it's neither a tautology, contradiction, it is a contingency. It's contingent on the truth values of full Q. Okay. But maybe we should look at examples of these. Like this is a tautology. This is always true. I mean, that's equivalent to saying this, and this is a tautology. It's always true. So let's look at some.
That's a symbol.
That's the not symbol.
Not symbol.
Yeah. So if you're writing in like LaTeX or you're using LaTeX commands in like Word or Pages, just it's not backslash not. So here we have some examples of compound propositions. Okay, so are any of these contradictions? Or any of these tautologies?
The first one's a contradiction.
First one, yes. This is a contradiction. Why is it a contradiction?
Because no matter what P is, not P is going to be the opposite, and it's an and, which means it's only true when both of them are true.
Right. So you have the conjunction and between P and not P. So P and not P. Since P and not P have different truth values, there's no way for both of them to be true. So this will always evaluate the false. What about B? What is B?
Tautology.
It's a tautology. It doesn't matter what you choose for Q, what truth value Q has, it's always going to be true because it has a false hypothesis.
D as well, right?
What?
D as well, right?
It's also tautology.
Yes, D is also a tautology. Because at least one of P or not P is going to be true, which would say that the or would evaluate the true. So this would also be a tautology. And then C is it's a contingency. You don't know until you plug in values for P, Q, and I. Okay. So we see that these things exist clearly. That there's all these will always evaluate to true. Some will always evaluate to false. And you would just write that by saying, so this would be like an identity. That's an identity. It's always true. You can use that whenever you encounter more complicated compound propositions, which we will. We're going to see combinations of a bunch of them, bunch of propositions together, and we'd like to reduce them down to something that's more simple to look at. It's easy to understand. Okay, let's see if we can discover another simple relation like this. Or more specifically, have you guys verify that it's the case. So this is logically equivalent to P and not Q. So use a truth table to verify that. You should know how to verify it. You fill in the columns and you show that they have the same truth values all the way down. So I claim that that's true. Take a few minutes to go ahead and do that. Okay, so it really is just as simple as verifying the truth table. So let's go ahead and do that. True, false, false, true, false, false. And so if P then Q, true, false, true, true. And then finally, let's look at P and not Q. Okay, so then we have true and false, which means it's going to be false. Then we have true and true, true. We have true and false, which is false. Then we have false and true. So false. Oh, wait a minute.
Wait, that's wrong.
That's
it. P and Q?
yeah, P and not Q. So P and not Q. So true and not that. So true and not false is true and true, true. False and false, false, false and true, false. Oh, so they are equivalent. My claim was not correct.
It's a contradiction. Yeah.
Well, it's true in one case, right? True and
Well, the biconditional, it's a contradiction, if that was the case, right?
so yeah, so these are. How can I fix this? Did I? Okay, let me make sure everything's fine. All right,
Can I ask a question?
yeah.
On the third row, it says if P is F and it's not true, that should be.
Well, let's go ahead and make another column. Let's make another column to make it more clear. I had everyone's saying different things, and it's throwing me off a little bit. So is it, I'm not telling you whether or not it's true or false. Do you believe the claim is true or false, based off of what you have on your paper?
It is false.
Okay, so let's look at not Q now. We just have to do this. There. Okay, so now we can like clearly see not Q. It makes it a little bit easier. If you look at P, then Q. So true implies true, true, true implies false, false, false implies true, true, false implies false, true. Okay, so are we good up to here?
Yes.
All right, so then let's take our time. P and not Q. Okay, P, so true and false. False. True and true. True. False and false. False and false. So it looks like we had the right entries. So no. They don't equal. They're not logically equivalent, because if now if we did the biconditional, it would be false all the way through. It'd be a contradiction, actually, would be the biconditional between those two. But can we change it? What do we notice about this column and that column? That's why I wrote this up here. What do we notice about those two columns? They're opposites. They're opposites. So then we know something. If they always have opposite signs, right? Can I just do this? Can I just negate that? So that becomes true, false, true, true. Ah, now I see something. I see that this column and this column are the same. See that? Yes.
So what you did is you just added a not.
Yeah.
To
and
the
then-
whole equation of.
Yeah, to the whole compound proposition, I took the not, and that not just changed the truth values, and now they equal. Now they all have this. Now the conditional, so now this side and that's like this and that have the same truth values. I wrote up one that was not equal, just so someone would say something on your own, because you're working on your own. You'd see that, oh, no, they don't. Anytime I write down claim, it's not necessarily going to be a true claim. If I write down theorem or something like that, then yes, it's a true statement. You can take it to be true. But if I write down a claim, it's up to you to investigate it.
Say it again.
If I write down a claim, don't take it to be true.
Oh,
It's just a claim. I never said it was true. Right?
So just to recap, now that the equation equals true, what do we write it as?
Oh, we would write the true thing that we discovered is that if P then Q is logically equivalent to the negation of P and not Q. That's what we discovered. The original thing was wrong, but we did find something by noticing a pattern that when we looked at this one, oh, it's always the opposite truth value. This is useful because what this tells us, and we'll learn more about this maybe the class after next, to prove or argue a conditional statement, if P then Q, it suffices to show P and not Q is a contradiction. Can someone explain what I mean by that? To prove if P then Q is always true. Okay, so when I say prove, I mean this. Show is a tautology, or show tautology. That's what it means to prove something. To prove something means you show that the compound proposition is always a true statement. It's a tautology. So if we, for whatever reason, we want to show something as a tautology, if P then Q in this case, why does it suffice to show that P and not Q is a contradiction? So how could we explain that? And what do I mean by that? It's right in front of you, but it's a little bit difficult to probably for you to see at this point. We want to show that this is always true. That's our goal in a lot of instances, actually. We want to argue that this is a tautology. Why is it the same to show that this is a contradiction? Close. It's because this is the negation, right? The negation of this is the original thing, right? So if this is always false and negated, we have this is always true. Does that make sense? So to show that this is always true, it suffices to show that the inside here is always false. That's what's called a proof by contradiction. When you have a statement that you want to show is true, you suppose the opposite and show that the opposite is false, which means the original statement must be true. And because this is always the opposite in truth value to the conditional, this is what we would show as false. We would look at that statement and then argue why the whole thing had to be false. Not this whole column, but like the compound proposition itself once you plug things in. Like just like this is always like this always worked out to be true, right?
Right.
But the opposite of it would be, what is the opposite? The opposite is, well, we know what the opposite is.
Not.
It's P and not Q is the opposite. So it would be the hypothesis and not that. So the hypothesis and not that, and that's always false, right? Like once we plugged in, like no matter what we plug in for Q, this is always true. No matter what we plug in for Q, this is always false. Yeah. There's again, like I'm trying to emphasize this dichotomy between propositions and their opposites. It's sometimes easier to look at the opposite than it is to look at the original. It's sometimes easier to argue why something is always false than to argue why it's always true. Right? So if you can show the opposite is always false, then the original must be true. It's like a clever way of getting there. Right? Like if you had some really like, imagine like you have like a really complicated, like who knows what's going on in here, blah, 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 really complicated. And you see like somewhere down the line, you see this. It doesn't even matter what's in there anymore because you got an and false. And that would be like, this is super easy to argue why it's always false because that. And so sometimes it's easy to argue things are false because of the way that the conjunction, the and operator works. Only one thing has to be false for it to like throw the whole thing away and the rest of it must be false as well. So that's why it's useful to know the opposite of the conditional is P and not Q. And then also though, we do also now have a way of converting between that and that. Right? If we have a conditional, we can convert it to this. And we can look at that. And you have a very vague sense of what I mean when I say this. I get that. But basically what we'll be doing next class is we're going to be arguing, building a bunch of theory behind logical equivalencies. Like building a bunch of identities, like maybe some of you might have done with like trig identities in like a pre-calc class. We're going to build a bunch of identities, which we will prove why they're equal by using truth tables or maybe some other means. And then once we know that, the next step would be to look at mathematical statements. Like for example, if n is even, then n squared is even. If n is even, then n squared is even. And that's a statement that we wish to prove always to be true. It happens to be true. But before we can get to mathematical statements, we need to understand the way that the logical equivalencies connect. Okay, so I guess think I want to stop here before I go any further because it really is its own lecture to talk about that stuff. So what I will say though, is that as far as reading goes, I would say maybe read over sections 1.1 and 1.3 from whichever version of the Rosen textbook that I mentioned on the first day of class that you have access to, edition 7 or higher. So Rosen, that's the author, Rosen, Discrete Mathematics and its Applications. Now, I can't give you a link to the PDF I'm using, because I just can't. But I literally just searched on Google, and it was like one of the top links to find a PDF for like the 7th edition. So you don't have to buy the book. You only have to buy the other book, the side book, which I'll also assign readings from that. So this is called Discrete Mathematics and its Applications. And I just searched Rosen Discrete Mathematics and its Applications PDF, and they popped up. So it is in the bookstore if you want to buy it. It is a great book, but it's also expensive. So you don't have to buy it. Just make sure, like I said, you get like, it's the 6th or 7th edition and higher, and you should be fine. I've never used the ones before that, so I don't know what they look like. I would just trust 6th and higher. Okay, and also you should get like a notification that I'm gonna put up the first homework assignments on the side book this week. They won't be due for like another 2 weeks, so there's no rush, but it wouldn't hurt to start. Right? So yeah.
How far should we be pacing this?
I would say the first chapter on logic, you want to like start now at least. I'm not going to start assigning things until like later this week, but you might want to start. But this book is great, and I really encourage you to read 1.1 and 1.3. It'll get you caught up to date. And that'll be it for today.
I would come from the, I would